So this is the second video segment from section 5.6. The last one ran a little long. I apologize for that, but I think 30 minutes isn't awful. I probably could have broken this up a little differently, but I'm hoping that I'll be able to do everything that I have left in maybe this last session. It may also be a little bit long, but I think rather than trying to sandwich 3 videos in being really short, we'll just do this as 2. And let me just move right over here. Now, what we did last time is we proved the 3 big the 3 big half-angle identities. And now what we're going to do, and then we also we showed how to find an exact value, which I think I've assigned some homework problems that do something similar. And I'll just say this, for whatever reason, when you're dealing with exact values, I have seen this happen so often that I think there's something to it. Just really, really make sure that you do that first step, which is where you say, okay, let me just kind of rewrite what we did last time. Remember, we had sine of 5 pi over 8. Now this is what people will do, which is just weird. They will not take this step because I guess for some reason it's unnatural. This is the step that people don't do, and then for whatever reason they go another route and they say that this is equal to plus or minus the square root of 1 minus cosine of 5 pi over 16, right? Which is not right. I mean, if you follow the steps the way I did them, it's going to be 5 pi over 4. But for some reason, people want to go the other way, and we talked about that when we were doing graphs, when we were trying to factor out the b value from a trigonometric function, that people often go backwards. And so you just have to be really meticulous and make sure that this is, that you're going the right way. But there's also another class of problems where we actually use the formulas. And it sounds very similar to problems we've done in the past, where you're given some information about a trig function, find some information about maybe some trig functions, and now of the half angle. So let me pose this problem. So suppose, excuse me, and maybe I'll mix up the argument. So suppose cosine of the angle S is equal to -3 over 7, and S is between pi and 3 pi over 2. So when you're working with and then I'll just go ahead and ask the questions. So find, let's say, sine of the half angle, cosine of the half angle, and tangent of the half angle. This is really convenient because we have cosine already, and almost every one of these formulas just uses cosine. So rather than using, I mean, with this one we have to have cosine of sorry, I used x's. It should be s. Apologize for that. Okay, I messed myself up. So to go back to this argument, every one of these formulas have a version that only uses cosine. So it's really convenient that we were given cosine. But supposing that we didn't have cosine, let's say we had sine or something like that, then we would probably want to find cosine first, cosine of s. Because this is sort of the key to using any one of those formulas. But since we already have it, we're great. Now, the one thing that we want to do is we want to focus on the quadrant of the argument. And specifically, we want to focus on the quadrant of the half angle. So note And I'm just going to divide everything by 2. Pi over 2 is, S over 2 is between pi over 2 and 3 pi over 4. Well, this tells you, right, that S over 2 is actually in quadrant 2. So that's gonna tell us which branch to use on all those formulas. Remember, every one of these has a plus or minus in it, and that's totally based on the quadrant of the argument. So we'll know that the sine one is positive, the cosine one is negative, and the tangent one is negative. So let's use those formulas. So first, we've got sine of S over 2 is equal to, now remember, we said plus, right? So I don't even need the minus here. It's going to be positive square root of 1 minus cosine of S all over 2, everything under a radical. Most of the time with these, the work is actually simplifying radicals, which I know everybody loves to do. Okay, so now what we'll do is we'll substitute the known value, where cosine of S is negative 3 over 7. So this becomes positive square root of 1, be careful with the SIGNs, 1 minus a negative 3 over 7 all over 2. Now that's numerically the correct answer, but this has all kinds of simplification issues. So we're going to first sort of deal with this thing on the inside. We're going to break this down to, we're going to get rid of this complex fraction by multiplying everything by 7 over 7, and then we'll clean up the radical stuff. So if I multiply every single term by 7 and just kind of ignore the radical for a minute, what I end up with is 7 plus 3 over 14, and of course that's still under that radical, which happens to be equal to positive square root of 10 over 14, which you've had, it may have been a while since you've dealt with rationalizing these kinds, but anytime you have something with the fraction where it's not in least terms, it makes sense to do that first. So we end up with plus square root of 5 over 7. And then now we're obliged to rationalize. This is much easier to deal with. So I'm going to multiply everything by root 7 over root 7. I'll kind of write that down here. We will end up with the positive square root of 35 over 7. Now to be honest, now that we have a single value of a trig function for this angle, and we know what quadrant it's in, we can just proceed to the old, draw a diagram, and this becomes the point on the terminal ray. There's a y value of root 35 and an r value of 7, and we could produce both cosine and tangent. But since we're wanting to work with these formulas, I'm going to go ahead and use them to find the other two values. So this is, I believe we're on page 5 now. Okay, so part B was to find cosine of S over 2. So recall the formula for cosine of S over 2, and because S over 2 is in quadrant 2, just a quick reminder, cosine is negative. So we don't need the plus or minus, we'll just write the negative sign. And this is the square root of 1 plus cosine of S all over 2. Again, cosine of S is negative 3 over 7. So this becomes negative square root of 1 plus negative 3 over 7 over 2. We're going to end up with that weird sort of radical again. So this reduces down, since we've already kind of done it, I'm going to multiply everything by 7 over 7. You end up with the square root of 7 now minus 3 over 14, which simplifies to negative square root of 4 over 14, which equals negative square root of 2 over 7. And now we'll rationalize this by multiplying everything by the square root of 7 over square root of 7. We end up with the net result that this is minus square root of 14 all over 7. Okay. Now for tangent, if we had sine in addition, if we had sine of s in addition to cosine of s, we could use one of those formulas that don't have a plus or minus. But since we haven't derived it, we haven't derived the value of sine of s, we'll just stick with either taking a ratio of these or actually use the formula. I would suggest we'll just go ahead and use the formula because we need some practice with it. So recall that tangent of s over 2 is equal to plus or minus. Now, this is in quadrant 2, so I can get rid of the, just like before, it's just minus. And that's the square root of 1 minus cosine of s over 1 plus cosine of s. And that will be the negative square root of 1 minus a negative 3 over 7 over 1 plus negative 3 over 7. Simplifying this again by multiplying all these terms by 7, we get negative square root of 7 plus 3 over 7 minus 3, which happens to be the negative square root of 10 over 4. And normally I would say you've got sort of a common term in this fraction, but I mean, that's a perfect square in the denominator. Let's not make too much of this and just realize that this is minus square root of 10 over 2, and it's as simplified as it needs to be. So there's kind of a sort of a semi-standard kind of problem that you might see in one of these sections where you apply the formulas that we've been given. There are other variations, but that's I think I might have assigned a couple. Now, the other thing that we want to be able to do, and there isn't going to be much of this in your academic life, but I'm going to go ahead and do a couple of proofs that involve half angles. So I'm going to state that as let's show that this perfect square, so sine of x over 2 plus cosine of x over 2, quantity squared, in fact equals 1 plus sine of x. That's kind of slick. Now, obviously, the left-hand side is more complicated. In fact, the right-hand side is reduced down to just about the smallest, most simple thing you can imagine. So let me start with the left-hand side. Sine of x over 2 plus cosine of x over 2, quantity squared, and I'll just distribute this. So this is going to be sine squared of x over 2 plus 2 sine x over 2 times cosine of x over 2 plus cosine squared of x over 2. It's a little cramped there, but I'll expand it here a little bit. Now note, this term and this term, they have the same argument, but it's sine squared plus cosine squared. There's a Pythagorean identity that tells you that those two terms combined together equals 1. So I'll go ahead and make that simplification and then make another argument here. So the rationale for this step here is actually an algebraic argument. We just simply distributed, FOILed that out. Now this argument is actually a Pythagorean identity. Finally, I want you to take a look at this term, because what you're seeing here is 2 times the sine of some angle times the cosine of the same angle. That's a double angle formula, right? For sine of 2 of whatever this is. So I've got 1 plus sine of 2 times whatever this angle happens to be, which happens to be x over 2. And that is a double angle identity for sine. And then we've got some simplification. I mean, we can do algebra inside these arguments, and you're just going to get that this is equal to 1 plus sine of x, which is an algebraic step, and that completes the proof. We started with the left-hand side, and we ended up with the right-hand side. Just a word of advice: anytime you're working with these double angles in a proof, it almost always makes sense to be working from the half angle, because you don't have a whole lot of formulas that allow you to take and go from an angle to a half angle. It's usually the other way around. I mean, you can develop them, but it doesn't seem a whole terribly useful. So let me try to do one more proof here, and it may take me this page, the rest of this page, and maybe even a little bit more. So let's show that tangent squared of x over 2 is equal to 1. Oh, this is almost immediate. What we're going to do is we're going to do this in, sorry, I had it. Secant, I was looking at the wrong target. Secant of x, got to be careful with the signs here, plus cosine of x minus 2 all over secant of x minus cosine of x. It's kind of an ugly looking thing over here on the right as well. So let me do this first. Let me just observe. This thing has cosines and reciprocals of cosines and whatnot in it. This has a couple of different ways that you could express this. And since it's squared, there may be a clue here that this is an ability to get rid of the square root that's in the first version of this. So let me just start on the left. And so tangent squared of x is equal to quantity squared plus or minus the square root of 1 minus cosine, sorry, that's x over 2. So plus or minus the square root of 1 minus cosine of x over 1 plus cosine of x. That's the first version. And since it's quantity squared, in some sense this will cancel out with this radical, and regardless of whether this was plus or minus, when you square it, it becomes positive, so that goes away. And what we're left with is just 1 minus cosine of x over 1 plus cosine of x. That's pretty slick. But I don't know where to go from here. So I'm basically going to now work from the right-hand side, and that'll be my target. Okay, and I'll start that on the next page. So we're on page 7 now. We wish to show that this bizarre looking secant of x plus cosine of x minus 2 over secant of x minus cosine of x, we want to show that that is in fact equal to 1 minus cosine of x over 1 plus cosine of x. And this is kind of, we went from the left to the middle, and now we're going to go from the right to the middle. So starting with the right-hand side of our original identity, secant of x plus cosine of x minus 2 over secant of x minus cosine of x. Now, to be completely frank here, I don't really know how to get there, at least not easily. So maybe what we could do is start by converting everything into sines and cosines. I'm going to make this really simple substitution for secant and then see where that takes me. So we end up with 1 over cosine of x plus cosine of x minus 2 all over 1 over cosine of x minus cosine of x. And that's just a reciprocal identity. So what I've done is I've created a complex fraction. And in order to get rid of the complex part of it, I'm just going to multiply by the reciprocal of all internal terms, which is just cosine of x. So everything gets hit with a power of cosine of x. So we end up with 1 plus cosine squared of x minus 2 cosine of x in the numerator. And in the denominator, we have 1 minus cosine squared of x. Now you're looking at that going, and this is just an algebra step. Okay, so you're looking at that going, well, I could turn that into sine of x and some other kinds of things. And that is true, but I think to finish this problem, we don't want to start instituting different trig functions. We have all the right things. We just have to figure out how to make that look like that. And what I'm going to suggest is I'm going to take a little bit of time here to clean this up, because this is not the way that you normally see a polynomial, right? It's not in ascending or descending order. So I think I'm just going to rewrite the numerator by moving some stuff around. So it's cosine squared of x minus 2 cosine of x plus 1. And then in the denominator, it's 1 minus cosine squared of x. So, and that's just, I mean, that's really simple algebra. Now, it just so happens that if you remember from the first lecture, I was talking about, hey, don't forget about factoring, because you can factor these things. And if we were to look at this instead of having cosines, if you just want to kind of think about this for a second as x squared minus 2x plus 1 over 1 minus x squared, where cosine is actually x, or you could use some other letter or whatever. This is a perfect square, and this is a difference of squares. So this will factor as x minus 1 over, or sorry, x minus 1 quantity squared over 1 minus x times 1 plus x. And you do have some cancellation that occurs here, but because the signs are different, I mean, here's the common factor, except one's negative of the other. So this will actually be a -1. Sorry, it doesn't wipe out the whole thing. It just wipes out the exponent. And so what you're left with is -1 times x minus 1 all over 1 plus x. And when you factor in this negative sign here, you end up with 1 minus x over 1 plus x. So if this was an algebra problem, this is what we would boil that down to. Now what's the difference? Instead of x, we have cosine of x in every place that x would appear. So to kind of to sort of set that aside, we would say the very next step here through this algebraic argument is that this is now equal to 1 minus cosine of x over 1 plus cosine of x, which happens to be where we wanted to get to. So again, this is just a bunch of algebra, and this is an algebraic step that, I mean, basically is repeating this algebra, but for a different, a different symbol that represents the variable. So I'd say that this proof is complete. I will also say this: there aren't in practical situations, there aren't a whole lot of applications for half angles. There may be some interesting. I mean, you now have the tools to be able to take smaller and smaller angles to find exact values, which is what medieval mathematicians and maybe even ancient mathematicians did. Is they would try to find the exact an exact expression for a smaller and smaller and smaller angle, because the idea is now you can you can infinitely divide an angle. So if you know what sine and cosine is for a 45-degree angle, or even a 30, or whatever else, you can now find what it is for half that, and then you can do it again and again and again and again. The formula just becomes more complex, but it's actually possible to arrive at the exact value and expression for it that has a lot of square roots and different ugly looking things, but those can be calculated. And so that's sort of as a finishing remark for this chapter, this is a technique that was developed over thousands of years to actually find numerical values for sine and cosine in smaller and smaller increments. And you can do that pretty much forever, because you can divide them up into a small piece and then start adding them back together using the sum and difference formulas and these half angle formulas, double angles, and it's really quite intriguing. If we had more time, I would talk about this more, but in the interest of brevity, I'm going to call it a day for this chapter. If you have any questions, concerns, those sorts of things, be sure to use the messaging system, and I'll also see you at an open session.